Hard. Okay. What? A bunch of. So I will let you meditate a bit about this question. No, not entirely trivial, not entirely hard. If I'll put a practice exam, I will put, like usual, more questions to practice among the homeworks. I'm sorry? Can you repeat? Yeah, there will be more questions in the homework. Anyhow, a question for you, not entirely trivial, not entirely hard. So something behind this question is that usually we think about, or they try to tell you that everything that is exponential is unsolvable and everything that is polynomial is solvable. And this question tries to highlight that there could be a lot of things in between. Like you can be exponential, but exponential not in n, the size of the graph, but exponential in square root n. So Independent set is a set of vertices as large as possible, obviously, such that if you have an edge in the graph, then from the two vertices of this edge, you can take either u or v, but not both. And here I'm asking for the maximum set, independent set. And you can have a running time which is exponential, but exponential is square root the number of vertices. So meditate a bit on it while we are stepping through the material. Okay, and beside it, I thought of going through the material from time to time, expand a bit, maybe I'll have association for related homework questions that I want to tell you more about it, but I don't have a too concrete plan for today, beside of, I made this big deck of slides that hopefully contains everything, and yeah. Something that I listed in the replies to the, I'll just stop the Zoom for a moment. Something that I listed in the replies for the previous homework was was the question about the Bloom filter, where we asked you had something like this. There, you actually had the other side of this graph, and we said that every leaf Li might store Si, which is list of songs, and it can be each leaf Lj is actually a user that might ask for a song out there. Typical case in the Casa. Or in the original Casa, when it was still not legit. And you were asked who has the song that I'm looking for. And we would like to send a query somewhere in this graph, but this graph has nice hierarchical weight. And we asked, how can I use a Bloom filter to make the query and the reporting of the song more efficient, right? I create, say, at Li a query, who has my song, and I send my query all over. And they want to pay, and every time that I send a query or send an update, because I might have more songs that I start storing, it costs me money, and I want to minimize the number of updates that I'm going to send and the number of queries that I'm going to send. Every time that I'm sending a message on an edge, I need to pay $1. So how can we use Bloom filter? Most people got most of it correctly, but we can squeeze a bit more from the Bloom filter. That what I stored in Li itself, I don't have to actually, because every Li knows which songs it has. But let's say that every Li also stores the Bloom filter of Si. Bloom filter of Si is stored in Li itself. Even though, as we'll see in a moment, it's not necessary, but maybe it's faster because the Bloom filter is much smaller, so I can keep it in the main memory, or more of it in the main memory and less of it in slower memories. Right, it's much, much smaller than the explicit list of songs. In the Bloom filter for every song, I just need 3-4 bits. If I need to store the whole name of the song, then I need a bunch of characters for it. And every character by itself is already 8 bits. So I'm much, the name of the song is obviously much, much longer than the number of bits that are dedicated for the Bloom filter of this song. So that was the Bloom filter itself that as we said, are helpful, but at a node. And now at a node V that has, say, L1 and L2, then what V will store is a Bloom filter of S1 union S2. But that's what I stored at the common parent of L1 and L2 is a Bloom filter of the two lists, S1 and S2. And we'll see how to update it quickly. And what I'll store that W over here, W is a grandparent of L1, L2, L3, and L4. W will store the Bloom filter of S1 union S2 union S3 union S4. Like all the songs that each one of its subtree has. And that's convenient. Why? Because I'm looking for the song remains the same. If I don't have it on my hard drive, then I'll ask V, do you happen to have this song? I mean, V doesn't store songs by itself, but if the Bloom filter of V that stores the Bloom filter of S1 and S2 says, yes, I do have it, then obviously I'll try to go to the other child of V. Not too many decisions in a binary tree. So more interesting, if my query reaches W, and W will say one of my descendants has this song based on this Bloom filter of the union. One of my descendants, one of my grandchildren has this song. Then now I'm going to ask V and V prime, do you have this song in this Bloom filter? Hopefully only one of them has it. And then I'll continue towards the child also. That is, only proceed among the nodes that I got a positive answer for. Of course, it might be that I need to visit both nodes, and it might be that because of the false positive, maybe I'll decide that I'll miss the song sometimes. But at least it is a strategy that if a query reach W, the song remains the same. When the query reach W and the answer is no, I don't have it, then obviously none of its descendants have this song, and there is no point of asking them about the query. Now, the beauty of the Bloom filter is that the updates could be quite small. Once I start storing more songs, I can either send the bits, just a few bits that are changing between the different Bloom filters, or I can send the whole Bloom filter by itself, or I can send the Bloom filter from V and V prime, and then the Bloom filter of the union is nothing but the bitwise OR of the two Bloom filters, right? You're just turning on all the bitwise of all the Bloom filters altogether. So, yeah. So that's how it all works very nicely. So just that people did get it right, but it's more about that updates are also very efficient. Okay, the question from homework 7 for monotone subsequencers. I send you my solution that was very straightforward, just two loops, where you are using the fact that it is a DAG What is a DAG? Sorry, I'm speaking. You want to say you have a node Vi. We want to look for a monotone subsequence that ends at Vi. What should I do? Among all the nodes that are to the left of Vi, all the points that are to the left of Vi and below Vi, I want to ask who has the maximum D of Vj value. I'll ask every node to keep some value, D of Vk, and D of Vk is a total weight of heaviest monotone subsequence that ends at Vk. That's the value that I want. That's the value that I want Vk to have. This. Remember, I'm looking for a monotone subsequence. It should increase both in x and in y. Each point has its weight. That has nothing to do with the height. Each point has its weight, and I'm looking for the heaviest monotone subsequence. So I think about it as a DAG. If I wish that every node has a directed edge to every other node that is above and to the right of this node. That's why it's a DAG. And we know that many algorithms work for DAGs if we are making sure that when we need a value D of V, in this case, this value D of V is already computed. Now, if you didn't create the DAG explicitly, it's fine, but it's easier to prove the correctness. If you'll say there is some underlying DAG here, even if I don't create of its edges straight ahead. And from now the algorithm is almost trivial. Access the vertices in a topological order. Since we have a DAG, we know that there is a topological order. And the topological order here just means if I don't have two points that have the same x coordinates, then the topological order just means access them from left to right, and essentially you're sure that any number, every edge that is created will be connected to somebody that is above it and on its right, so you cannot ignore the y value. But the topological order itself is fine to ignore. You're just saying for every edge that exists, the label, which is nothing but the x coordinate, the label of the first one is smaller than the label of the endpoint of this edge. So a straightforward approach would be for I goes from 1 to n, and for j, or for n, I goes from 2 to n, for j goes from 1 to I minus 1, d of vi equals the max of d of vi, w vi plus d of vj but yeah, let me insert something here. Sorry. and j, if y of pi is larger than y of pj. And I know that the x value is satisfied because pj is to the left of pi. Then d of vi equals the max of d of vi, d of vj plus w pi. Okay. So that was n squared. It's also nice because it's easy to actually implement it with the right data structure. And with the right data structure, this search is just taking logarithmic time. When I'm only looking for points that are to the left, what is the heaviest point, which is to the left of me and below me. Okay. Other things, questions from you guys? Zoom people? No. Okay, we will have probably a review. We said it maybe 2 days before the midterm, like 5-ish. If it works for you, we'll communicate by email, but that's a default. I mean, if you prefer different hours, it's fine. I'm just afraid of conflict with other things that you have. As usual, if you have something terrible, that if you have multiple exams, finals at the very same day, come and talk to me. Maybe we'll figure a bit more time. I don't know if I can do something if there is something 1 day before, but definitely it's the same day. I think that 2 exam is deadly. What do we have in the material? Let's zoom through the slides. Sorry? No, I should remove it. We decided that, fortunately or unfortunately, people knew Kruskal already, and I'm trying, yeah. No, we will not have Kruskal because Kruskal is interesting when we have a union find with it. And to do union find, we can do it with log n or use amortized analysis. And then the running time of each operation takes alpha n, but it takes some time to show. So we skipped it. Okay, multiple hash functions where we use it for distributed databases. We have it, of course. In the material, maybe here is where the material is coming. Dot product will be in there because too many mistakes happens when I asked you about it in the midterm, so it's a good opportunity to rehash it. How do we do the bit product? What guarantees that the dot product will work? And why the dot product creates a uniform, a universal family of hash functions. Again, people got a few midterms were not great about it, so let's ask it again. What constitutes a universal family? Why is the dot product is universal family? When we are using the dot product, there is various ideas that you have to keep in mind, like that M should be prime, and there is a reason for it. The constants should be between 0 and n minus 1. The keys that you're using should be between 0 and n minus 1. Why does it all happen? And it all happens to guarantee that, as this slide shows it, if I need to create my function by picking 2 constants, alpha and beta, then if alpha, one of my coefficients, is already chosen, or if I have more elements in my dot product, then alpha 1, alpha 2, alpha 3, yada, yada, they were all already chosen. And I can count how many ways do I have to keep to choose alpha. Alpha would be about a minus 1 or would be actually m if I allow 0, m minus 1 if I'm not. And after I chose it, I'm asking what is the probability that I'll pick beta, the other part of the hash function, so I will have a collision between two keys. I'll assume that somebody gave me two keys, and I'm asking how many functions create a collision. And the whole obsession with using prime numbers, or at least relatively primes, was to guarantee that for every alpha that I'll pick, provided that the keys yi and yj are different, for every alpha that I'll pick, there will be at most one beta that caused these two guys to collide, which is the number of solutions of ax equal b modulo m. So I ask here, I rehashed this point a few times in the homework question where I ask you how many solutions do you have to the equation ax equal b modulo 8. And it turns out that for some base you don't have solution at all, and for some base you have multiple solutions. So that was, once it's not a prime, it doesn't mean that it will work necessarily bad for your hash function, but it means that it doesn't come with guarantees that it is a universal family. So there is a higher chance, I would say, that for your data, this family will not behave well. OK, and I'll get back very soon to the dot product. Why is the dot product the definition of universal family? People confused all the time between that universal family has to do with that it's not universal family if there are collisions at all. I saw some answers like this. That's, of course, wrong. Every hash function has collision as long as the domain is larger than the number of slots, just pigeonhole principle. It's wanted, the universal family said that no matter which pair of keys that I'll pick, as long as they are different, there are not many functions that creates collision between this pair. That's all it says. And yeah, we went through it multiple times. And we wanted to say that essentially, out of all the hash functions, for every pair of keys, out of all the hash functions, the number of hash functions that caused this key to collide with this key will be no more than 1 over m, the total number of hash functions. And the example that I liked to show was that if I have my table, hash table that now I draw it horizontally, where this would be cell m minus 1, this will be 0. I placed k1 somewhere, ki I placed somewhere. I have to be inserted somewhere in the table. I want to insert k2 at some point, and before I insert k2, I want to pick a hash function that I'll use out of the family. Right. So if I just toss k2 randomly into the table, no hash function at all, just pick an element of the table and toss k2 into the table, what's the chance of a collision? 1 over m, because there are m cells. If instead you are deciding where k2 is going to be hosted by, let's pick a hash function that will take k1 to one cell and will take k2 to one cell, but this way we decide where k1 and k2 are going to be hosted. What the chances of collision if the family is universal? No more than 1 over m. It's not worse than just tossing these two keys at random into the table. And since I don't know what is my data, that's essentially as good as I can hope for. That is that for any type of data, it will not, for any type of data, what we are getting from it, without knowing anything about your data, what can I do if I want to spread it as evenly as possible? I'll just toss it uniformly among all the cells, essentially pick for every key a cell at random if I don't know anything about the data. It's not very useful data structure because I cannot retrieve it, but that at least minimizes the number of collisions. But keeping in every cell 1 over n of the, n over m of the keys will be just evenly spread the keys. What the universal hash function or universal family trying to do is to say that even though I don't know what is your data, the impact, once you pick a function, you will expect the same distribution of data, but you have the advantage that, hey, you have the hash functions that you can retrieve the data if you want to ask this key exists or doesn't exist. Okay, enough about universality. Just repeat it because we talked about it so long. A perfect hash function, also something that we saw a lot of time. What happens with universal, what happens with perfect family, you know the data ahead of time, only then you can solve the hash function. You can create a huge hash table of n square size, and then you don't have collisions at all. With probability of at least half, you don't have collision. Now, why are we obsessed with so many algorithms with probability half? Is that because we can amplify it. If we'll repeat, if something happens with probability half, and we can check if it happens or doesn't happen, then if it fails, then we'll try it again. If it fails, try it again, and after the chance that we'll fail with our experiment k times is not half, it's half 1 over 2 to the k. So we can make the probability of failure as low as possible. That's why we are so proud that we brought something to probability of half. So once again, we can create the main table of size n of size n squared, and then with high probability there are no collisions at all, but the memory is ridiculous. Or we can use 2n slots, m which is roughly 2n slots, and then there will be collisions, but every key will collide with high probability with a constant number of other keys. Again, every key with high probability will collide in constant number with only a constant number of other keys. It's not realistic that my first attempt, when I have 2n slots, there will be no collision at all, but it is realistic that the number of collisions that every key is involved in is, remember, the average is half. So some of the keys will be completely by itself, some will be with 1, 2, 3, but it's rare to find nodes that will have a lot of keys colliding with them. What are we doing next? We look at all the keys that collide, all the keys that do collide in the first hash table, and now we can allocate another hash table for only these keys, and the size of the second hash table is quadratic, is n squared, but it's not the original n. It's only the n of the number of keys that collided originally. So we can afford it because it's n squared, but of a constant, small number, so it's still quite small. And when we are doing, and the same for individually for every equivalent group, every set of keys that collide with each other. And then we made the math, and so that the overall expected size is only linear. And of course, at every step, we are using universal hash function, or else. Or hash function from universal family, to be precise, which would guarantee that the average number of collisions will be order n. People cool with everybody? And if not, then yeah. We discussed this case, just solving by open addressing, stuff that I'm sure that you've seen in previous courses. Why do I want the table to be prime? I don't necessarily want it to be prime, but if it's not prime, then I need to be careful that if I have a probing strategy that performs jumps, you had a homework question about it. If I have a probing strategy that performs jumps, well, if the jump is 1, just check the next element, the next element, the next element, and it's just linear probing, which we discussed a few times. Linear probing is a disaster. Theoretically, it works quite well in practice. Remember why? No. Remember why theoretically disaster is easy? Because it means that once we have a cluster, then the next element has a good chance to join this cluster, to make this cluster even bigger. And once I have a cluster, once I have a cluster, namely a set of cells that are all C together, it might be not the only cluster, but it is one of them, and I insert a key, and this key happens to hit any of the elements of this cluster, it, with probability of 100%, will just make this cluster a bit larger here at the bottom. Making it even worse. And now, what's the average time to search an element in the cluster? You pick an element, and then you start going down, down, down. You have to potentially go through all the elements in the cluster, on average half of them. So that was all bad-mouthing linear probing. So why is linear probing works in practice?
Load full blocks of memory at one time.
Yeah, but our computer doesn't like to bring from slower memory an individual element. It likes to bring big chunk of memory, and since we want to implement hash tables in arrays, maybe contiguous pieces, blocks of memories that will be all mapped together, then you have great chance that if you're checking this element, then the next element is already in your cache. And the next one is in your cache, so you will spend much less time. So it's potentially worse this time. That is, as long as your hash table is small, then everything fits in your main memory and you don't really feel the difference, and then linear probing is slower, but if everything fits in your main memory, then you don't need sophisticated data structure. Right? It's not huge amount of elements. But yeah, but it's important to remember that theory, in practice, theory was only that much in practice. But in theory, practice, yeah, we're not going there again. Okay. We talked about leaving a dummy. Talked about the probing strategy. Why I don't? Yeah, I started to tell you why I don't want jumps. Sorry, I'm not in the right slide. But why, when I'm using secondary hash function, double addressing secondary hash functions that perform jumps, that is, my hash function would be of the type age of ki would be something like age1 of k plus I times age of k. And all of it as usual mod m, which means that I look at the first place that k lands into, and if I don't find it over there, then I perform a jump of some number potentially different than 1. If it's 1, then it's just linear probing. If it's 0 that you had the homework on, then you don't make any progress, and it's very sad. If it's 2 or more, then you're performing a constant jump that depends on the different function. And it's a way to avoid this clustering of linear probing, because then some keys will get to different. The fact that 2 keys meet in the first cell doesn't mean that they'll meet in the next probe, because they has a chance to jump to different locations. And with this strategy, the only warning was make sure that age2 of k, the size of the jump does not divide the size of the table. Like, if the table has 8 slots and the jump is of size 4, then from location 4, I'll jump to location 8, which is 0. And if this is occupied, then I'll jump back to location 4, and then to location 0, and location 4, and location 0, and then I'll give up and claim that the table is empty, even though it's not. You had a question about it. Makes sense, right? Why we want this H2, why we want H2 first to be different than 0, and secondly to not be a divisor of M. And one way to obtain it was to pick M as a prime. Okay, enough. Maintenance, probing, double hashing, we talked about it. Expected number of probes, please remember this theorem. What is the expected number of probes? Why does it follow this formula? That want to say that if every probe lands somewhere in the table, and every location at every probe is equally likely to land in every cell, then here is the calculation of what the probability is that you'll need one probe only. When do you need one probe only? Well, if the key that I'm after is not in the table, which is the slowest case, then the only way that I'll need one probe only would be, it's success, but it's success in the sense that I can stop the search on my first try because I landed on a cell that is empty. Then that will happen with probability, which is what's the ratio between empty cells versus the total number of cells. If alpha of the cells are empty, and 1 minus alpha, so if alpha of the cells are occupied, 1 minus alpha are empty, that's exactly the probability that you need one probe. What's the probability that your first probe landed on an occupied cell, but the second on empty cell? Exactly this one, and then you need one probe. 2 probes, 3 probe, J probe would be with probability alpha to the J, 1 minus alpha. What is the expected number? This summation, which is not exactly geometric summation, but it has its own formula, but if when alpha starts to be larger than half, then I need to show it as a logarithmic scale, and this number goes really, really fast to almost the whole table. That is, the message from here is make sure that your table is at least half empty. Okay, cuckoo hashing. We didn't get very deep into the analysis, but I still want you to remember what happens with cuckoo hashing in terms of main algorithm and in terms of what's the advantage of it and why we expect it to work. So advantages is that when I'm searching for a key, it will take me a constant time. If I use my database in a way that bias searching for key more than just insertion, or even if it's the same number, it's really nice that I can, with probability 1, find the key that I'm after, or decide that it's not in the table, all in a constant time. There is a beautiful video that I'll share with you that talk about cuckoo birds. It's not one particular type of bird. It's actually behavior that many birds share of getting rid of other eggs in their nest that they want to use. It's actually completely fascinating. Like there are ones that tries to damage previous owner's eggs. There are types of birds that actually lay particularly heavy eggs that has a chance to handle a crash, but have a good chance to damage the original hosting. So what was the idea? So we're using two hash table, and we are inserting some number x1 into the cell. Why is this going to this cell? Because age 1 of x1 equals 2, so I'm inserting x1 into this cell. And possibly for the very same reason, x2 will be inserted into this cell. So I'm using two tables, I'm using two hash functions, one for each. And this hash function better be different than each other. And now I insert x3, and it happens that x3 is going to collide with x1. So what do? I take x1 and keep it in hand in a moment, and keeping x3 over here. So I'll just write that x1 used to be here and was deleted. And I insert x1 into the other hash table. So I'll compute age2, the other hash function of x1, the one that just was removed from its nest. And let's say that it goes to this cell, x1. So h2 of x1 happens to be 1, so x1 is here. And in this sense, I created an edge between these two nodes. Now, what happens when I'm inserting yet another key, maybe to x2, maybe to, doesn't matter which key will it be, it is going to eventually collide with x1. It's going to collide, say, with x3, just to show you why things are working. I'm inserting x4. That's actually a simpler example. Insert x4 and age1, the first hash table of age1. Age1 of x4 happens to be 2 once again. To collide with x3, that collides once again. So x3 is going to be removed, and x4 is going to take its place. What do I do with x4? I'll compute what is age2 of x4. And now, what I hope my hash function to do, because I'm using different hash functions for the first table and the second table, is that it's possible that age2 of x4 will be 1 as well. So x1 went to this place, and x3 that is just removed will go into this cell as well. But hopefully, x3 will go and sit down in a different cell. So we are using the fact that two keys collided on the first table doesn't mean anything about their chance of collision in the second table. We hope that the chance of collision in the second table is not larger than the chance of collision of any two keys. Again, the fact that two keys collided originally in this cell doesn't mean that they'll collide later. And later on, I can take x3. If I want to insert somebody over here, x5, then I'll compute age1 of x3, age1 of x3, that will take me back into this cell, moving x4, and so on. So you see that there is a set of transformation where a key might move back and forth, but usually it's okay. Usually a small path of transformation is not too bad. Now, the big invariant is that for every key, it's either in the first table where H1 told you to search for, and there is no second probing in the first table. That's the only two locations that x1 can be is either at the second table at age 2 of x1, if it's in the second table, or in the first table at age 1 of x1. And that's the reason that we are not letting x1. Why do we need this cuckoo behavior? This cuckoo behavior is, what is a cuckoo behavior? It takes the eggs that exist in the nest and pull it out, and instead it puts its own egg. Why do I need it? Because if I will try to say, I moved x1 from here to here, now somebody wants to go into this place, let's insert it into the first table, but where x1 want to be inserted, h1 of x1. Well, I moved x1 out from here. It already was kicked out of its nest once. It will try to go into a nest that is already occupied. I stop only when I landed a key in an empty cell. That's why I keep the key at each iteration. So maybe x1 moved from here to here, but it kicked somebody, and somebody that was kicked will not take me back with high probability to the same cell, will take me to a different cell. Maybe I'll kick another one, which will take me to a different cell as well. And as long as I don't have small cycles in it, which happens in high probability, as long as I don't have cycles in it that A kicks B, kicks C, kick D, kick A again and again, and this cycle will go forever, as long as you don't have cycles, everything will end quite fast. So the expected, as long as N is, as long as you are using 2N memory, that is half of the cells are empty, each one of the arrays of size N, half of the cells are empty. As long as you're doing it, then the expected time for an insert is order 1, like in normal hash table. But the expected time for find is constant. Only 2 places that the key might be. And again, in the take-home message is, why do we think that we are not just alternating between the same 2 cells again and again once we are inserting an element? Right, I want to make sure that this point understood well. Let's assume that I keep x1 here, I insert x3, I'll take x1 to the different place. Now somebody wants to go into this place, and I'll instead, and I'll take x, and I'll compute x1 again and ask what is its hash function. Wait, no, if x1 is here, then I am good. The only other place that x2 will be is when it's going to kick x3 now from this cell, but x3, once it's being kicked, will not go to where x1 is. That is, it's unlikely that x1 caused x2 to be kicked, and x2 in turn caused x1 to be kicked. And this cycle of 2 elements go forever and ever. And still show that I've once again, my last attempt to say it. X1 inserted originally, X2 that is coming, try to hit this location, busy, so I'll move it to X3 because this location is busy, trying to insert somebody into X1 that will be inserted somewhere. If I'm trying now to insert somebody else, collide with X1, first the second location of the somebody else is likely to be X3, is likely to be X4 and not X3, because even if they collided in the first location, they are not colliding in the second location. And secondly, the fact that two keys collide on one table doesn't increase the chance that they'll collide again in the second table. Actually, they're more likely to go to different locations. So quite a slow chance of long cycles. OK, and we didn't prove much of a theory about why there are no long cycles and a lot of long cycles in this part. It's, you can still definitely use it without going through the wheel understanding. OK, we talked more about Bloom filters, even though we skipped some of the theory there. Just basic idea of Bloom filter, you know. Keep a few hash for every key that is arriving. Keep k hash functions that tells you indices that needs to be turned on once the key x is inserted. Key x is inserted, you're applying age 1, age 2, age 1, age 2 that's missing here, age 3 that appears, tells you what are the bits, what are the indices in the table that needs to be turned on. And k is about 3 or 4 in practice. The number n of bits will be how many keys do you hope that the table will store times 4, about 4 bits per element. Again, where is a big save up in memory that I don't store the strings, the song remains the same. I just turn on a few bits. To check if the song remains the same is in the table or not, easy. Just you know, check if they compute the corresponding bits and check if they are on or off. That's kind of easy, and there is a chance that you'll make a mistake and you'll repeat that in one of my router, the song remains the same is there, even though I said that it's not. But we didn't do the math. We will believe the experts claiming that the probability that it happens, of course, if you are using universal hash functions that are from universal family, etc., we think that the hash, that every bit is turning on or off kind of at random. Every bit has the same probability to be picked. And when we are comparing it, one of the questions that I ask you is pros and cons of Bloom filter comparing to normal hash table. So first, the good and the bad is that it's 4 bits versus an alphanumeric, or at least a longer key that commonly will take at least 64 bits, say if it's just long int. Possibly much more. It doesn't tell you, it might make an error, positive error only. It will never, if it tells you that in your database, the song remains the same is not there. There is no mistake, then the song remains the same is definitely not there. But the opposite doesn't necessarily hold. That is, it might have false positive. That's why we think about it as a filter. It filters a search in the tree that we had earlier, that instead of doing epidemic search of asking everybody, every router, hey, do you have the song remain the same or not? it helps us get subgroups of routers that there is no point of searching. They definitely don't have it. Okay, so it's making the search in the slower memory, especially if it's distributed, much, much more efficient. To update it, other tell me that is I just stored a few songs. How can I update the Bloom filter? I can either send the whole Bloom filter because, well, it's long, it's still a large array, but it's much smaller than the copy of my memory specifically, obviously. And then I can do updates by just bitwise OR. Just turn on the bits that are one of my two children have. So it's easy to do this part. It's also easy to do intersections. What is intersection? It's bitwise AND. Just turn on. Instead, I have two routers. What are all the bits that both of them? What are all the songs that both of them have? I don't know which songs they are, but I know that they are represented by the Bloom filter, which is what? The Bloom filters of each router independently, and then do bitwise AND. It must be, as long as you are using the same hash function, it must be bits that are turned on in both locations. And that it actually goes beyond it, that you can approximate or guesstimate by it the number of elements that exist in the hash, in the Bloom filter, how many elements it represents. You want to know for two routers which documents they both have that share the same words. It will be the number to know how many songs you have. It will be roughly the number of songs that you need to estimate in the first router, plus the number of songs that you have in the second router, minus the number of songs in both of them. So in all cases, if you have the Bloom filters, you can have good guesses about where do you have a document that touches this list of topics, right? That have words that touches a long list of topics. You're doing a search of a long list of topics, all the documents that contains algorithms and Bloom filters are out there, so it needs to include both Bloom and filter and maybe other words that I can throw in, take all these words, create a Bloom filter, and yada, yada. Now you can search through it through a big set of documents. So very useful trick. People, any idea about this, how to get to this running time? It's a question that you should be able to solve. You want to find an independent set in a graph is, and I allow exponential time, but I want exponential time. It is nicer. And no approximation here. I need Zoom people, live people. Hint, it's related to topics that we discussed in dynamic programming.
Maybe we start with the complement.
Okay. Go ahead. I mean, we use the complement heavily when we looked for clicks in graphs, and we used ILP. So that was useful there. I am not sure that it will help me here. I understand why, and then in the complement I see you're looking for click. Yeah, I mean, so it converted to a different problem, I guess, for clicks, but I don't see. So just to remind you, planar graphs are graphs where you can draw them in a way that there are no edges that cross each other. There is a lot of geometry that we did not discuss in this course, but there was one big property that we did discuss. Yes?
I didn't have all the details, but you could find some planar separator, and then you have two subproblems to solve.
Fantastic. You almost nailed it. So every intersection is a vertex in this planar graph, an example of planar graph. And our first step for planar graph, what would be study about many of the dynamic programming problems, is that many graphs, not only planar, but planar are very well known for it. You always have a balance separator of at most square root n many nodes. That is, there is a set of square root n many nodes that if I'll remove them with all the edges that are connecting to them, I'll break the graph into two or more parts. And every part has size of at most half of the size of the graph. It's actually a bit less. But every set will have a size of, let's say, at most 2/3 of the graph. It's more accurate. So if you're confused by the 2/3, assume that I broke the graph into two pieces, that each one at the moment it's good enough. I have n-half many vertices. So that would be my separator. Notice in this case there is exactly square root n. If I have square root n many rows, square root n many columns, this size will be square root n. And where is the divide and conquer happens here is I will try to assume that this vertex and this vertex and this vertex, this belongs to the independent set. That the blue vertices will belong to the vertex independent set, and when I'll remove them, of course, I break the graph into two pieces. And notice that there is no edge that goes from the right side, no edge that goes from the right side to the left side. So, of course, I'm looking for independent set of everything, but I'll start by iterating all the independent set of the separator only. How many choices do I have for independent sets at the separator only? Well, there might be edges in the separator, like in this case. But even if the separator, no two vertices of the separator are connected by an edge, how many choices do you have? How many different separators? Well, if there are square root n many vertices, then you have 2 to the square root n many different independent sets that you want to check.
Do we need to account for when none of the element in the separator is belong to the independent set?
Even though it's still making it a separator. So now you'll say, sure, I'll take actually the separator plus the little vertices that I have to the left and the right, and I'll iterate over them. But once I take the separator plus the one hop away from the separator, I'm still in square root n many vertices. And I'll iterate over all of them. There is a bit technicality, but the main thing is that things that happen, decisions that you'll make on the right are independent than decisions that you'll make on the left.
I forgot. How are we finding the separator?
I did not teach.
Oh, okay. So
there
does
are-
that add to the runtime if you include it?
Yes, but you can do it in polynomial time. And you can even find the minimum separator in polynomial time, not exact, because it can't be hard, but a good approximation. But yeah, it's neglectable comparing to these enormous running times that you see over here. So the big idea that you want to take from here is that you can have a big exponential on the number of vertices on the separator itself, and now you have pretty much some vertices next to the separator are also influenced, so you want to iterate over them vertices that are just connected to the separator, but everything else, you know. The decision on you will find the maximum size separator on the right side. I mean, after you decided what is the configuration of the separator, you'll try one out of the so many, exponentially many, configuration of the independent set on the separator itself, solve the problem optimally on the right side, solve the problem optimally on the left side, and the number of vertices in the left and the number of vertices on the right plus the vertices on the separator is exactly the size of the independent set. And when you're looking for optimal solution on the left side, you couldn't care less about what happened on the right side. So it's similar to, in a sense, picking the separator is like picking the diagonal in the polygon triangulation. We talked in the dynamic programming about the polygon triangulation. Yeah, play with this. Okay. Rabin algorithm, Rabin-Karp. We played with this. You had a question, homework question that asked how many primes do I need to collect if I want to match a substring of file 1 to a substring of file 2. So you had a homework question that says, here is file 1, and I look at a substring S of I. Here is file 2. And I look at substring of the same length Sj. J tells me by how much did I shift it. So that's index j and that's index I. How much did I shift? And I take the same length of substring, both of length L. Strong substring that I ask, and I want to ask, is there any shift over here that matches any shift over here? So, and Rabin is doing a few very smart tricks on its way. Well, one is that it says it's much easier to compute if L is long. It's much easier to compute the hash, to first compare the hash values of the two substring, and only if the hash values match, only then I'll check them one by one. And Rabin actually didn't take about 2 files. It was 1 file and 1 pattern. But in the homework, I asked to extend it. So it's easy to compute the hash value. But if I use most of the hash values, it doesn't help me very much, because to hash L characters, I need omega L time to individually treat each one of the characters. Rabin says, take in particular this hash function. why is it so preferable to use this hash function? Actually, takes this value, which is a binary representation of what you got here, modulo m. I could have worked with any base, 8, 10, whichever. Take with any base, but still represent it as a single number, and then do modulo m. Well, it's not coming from universal family in any way. Different hash functions, still very useful. Why is this useful? Because now when I do the shift by 1, I want to shift it to location j plus 1 rather than location j, then I can do it in constant time. So that was the first point to remember, that even the hash function might be more great or less great, but the computation time of shifting the table is only a constant. That's why the solution, for example, is preferable over suffix trees that some people suggested to solve this problem, which is not a bad solution. But still, every shift, I needed to check each one of the characters independently, always starting from scratch. OK, so that was the first trick. The second trick was that, of course, I don't work with a big number itself because it could be huge. I work with this number modulo q. And then when I'm moving the shift from j to j plus 1, or from I to I plus 1, it's a constant time. The solution to the homework question, by the way, was compute all the shifts over here, compute all the shifts over here. You're getting altogether n plus n many shifts. Put all of them in a hash table and see for collisions. Right? At this point, you couldn't compare one shift to one specific element, but instead, you're asking either any shift here that matches any shift over here, I and j. And the solution for it was just the same solution like in the independent file. Yeah.
I think you asked a follow-up question in the next comment about the probability. I don't remember. Did you ever go over the answer to that one?
No, let's go over it now. So it was,
We are over time.
yeah, but.
I'll stay if you have time to answer it.
Sure, let's at least go finish at this point, and then I'll say another few words. By the way, I can stay more if it's good. So the big deal was that I look at any of these numbers and ask how many different primes can divide it. And here I will use that the number will be represented as a binary, as x, thinking about it as a binary numbers. And on the other hand, I'll do the prime representation of each one of these numbers. So I have a false matching if the values that I'm getting from here, modulo q, equals to the value that I'm getting here, modulo q, which happens only if this minus this is congruent equal to 0 modulo q, which happens if and only if q, that q over here, is one of the primes that divides x. X is a gap between this and this. And the very clever argument was that since in the prime representation, each one of the pi's is 2 or more, then the total number of bad q's cannot be more than the number of bits that I have over here. Right. The number of the different, each pi is at least 2 or larger prime. So there will be at most, if you have L bits over here, there can be at most L bad primes. OK, and now, and here I'm different than the original slide. The way that I proved how many, what's your choice in the original Rabin algorithm. What's your chance to land on a bad prime? Let's collect all the bad primes from this case, and we are collecting m is a length, or you know, to be in the same notation with Robin. Let's change this to M, the length of the pattern in both. So I collect M bed primes from the first shift, M bed primes from the second, all the way up to M bed primes from the last shift, where the shift is at index n minus m. So altogether, I collected n bed primes. In this case, and I don't want to have to pick Q, which is any of these bed primes. Now, of course, a chicken or an egg. Originally, I don't know what the bed primes until I checked all these options. That's why I picked Q at random. And it's quite likely that Q, and it's possible that Q will be 2. And 2 divides a lot of the numbers that you'll get. So, and in this case, you just realize it's not a good prime, but I have plenty of other primes that I can use in the set of primes that I defined. The only difference that happens here is that I'll repeat this collection of bed primes, not only from the shift of P, but also from the shift on Q. So I still, the only difference is that now the number of bed primes is M per every setting times N for the shifts of P times N for the shift on the other file. Yeah. And that's actually people nailed very well, that you want altogether that the number of primes that you'll pick is generate a set of 9 times M times, now instead of the N over here, you'll write N squared. A quick note that if you want to go, was mentioning people got confused between in the homework. Had a few confusions, not typical, but some people got confused between dynamic time warping and Frechet. They are both involving dogs and both involving lengths of a leash, but there is big difference between them. Right? One said, what is the maximum length of a leash? And one asked, what is the sum of lengths of the leash? And in the weak Frechet, or the weak dynamic time warping, weak Frechet or the weak dynamic time warping, where they can move backward and forward, I suggested to think about it as a graph. And in this graph, we can move from a node ij to any allowable other nodes. If they are only allowed to move forward, then I go from ij into ij plus 1. If the one allowed to move backwards, then there are edges also to the I minus 1, j minus 1, etc. And now, some answer that I got was that I just asked for connectivity in the graph, which was a very wrong answer, because it's the correct answer if I ask for the Frechet case. I write for every vertex allowable or not, the distance of the leash is too small or too large. But, and then check for connectivity. If you ask for the weak dynamic time warping, that you're summing up the lengths of the leashes, then you sum up the weights of every vertex and find the shortest path. Via Dijkstra, for example, with a little caveat that the weights are on vertices, not on edges. But you know how to handle it from the days that we handle flow. I'm happy to continue with the slides. I'm happy to call it a day and do other things, solving your questions. We will have more chances to meet and hang around for the week, and we will have more review toward the end, toward the midterm. But if there is no specific stuff for me that you want, from the slides that you want me to go over, I think that we are good. I fix the slides at the very end. How do I go fast in it? The slide at the very end for the minimum spanning tree. Now it makes sense. For the greedy two centers, it also makes sense. Different notation. So now it make it, yeah, it's, oh, easier to follow. You have it fixed, which I can go or not. I think that it's quite simple. Call it a day. Sounds good. Thank you. I don't know, really important things. I try to make this course to use a little academic freedom of finding the thing that will be the most useful for us. You heard me already giving this speech. Was trying to look for the things that are relevant to the material, but also score quite high on my scale in coolness and score quite high about the chances that you'll use it in the future. And so I made a few experiments. I don't know if they were all successful. But yeah, at least that was my attempt in picking the material and stays a bit less from the mainstream of teaching you in the 15 times Dijkstra again and Bellman-Ford again, and so on. For me, in my research career, for the little that I know, hitting the multi-commodity network, multi-commodity shortest path is much more common than just the shortest path itself. Every edge has 2 parameters. You know, you want to go from here to Phoenix, but also to see a lot of things along the way, and also to be fuel economical. So every edge has different parameters, and you want to find it, which makes the problem NP hard, but it was one of the things that was important for me to mention. You can apply essentially, if you keep applying relaxation of the edges at any order that you want, for example, use something like Bellman-Ford. It is just very, very robust algorithm. You can massage it, hit it in various ways. It will still work. Go over all the edges, do relax. Go over all the edges, do relax. Keep on doing, since it's NP hard, I'll not tell you when you end exactly. There are cases that I can tell you when you'll end. For example, if one of the criteria, as in the homework, was how many hops you have as well as a weight, then I can say that, then I can guarantee that after n hops, or n passes of the edges you do. But yeah, that's one problem that I thought that deserve much more attention. Set cover, I gave more attention than in general course. Ochbaum and the budget set cover that CLRS doesn't cover. CLRS shows the log n approximation, but doesn't show what I found much more important than the case of the bound of the 1 minus 1 over E. For the budget case, you just have K sets to pick what are you doing the best of them, and the result that is very easy to show once you're going through the material. We didn't show it exactly. If you're going through everything here and then you're saying at the case step, I know that AL will not be exactly the optimum, but will be this optimum times beta L, because I don't know what is the largest that I can pick, but I know that I can pick at least 90% of the optimum at each step, and then without a proof. It will boils down immediately. It's completely straightforward into, instead of the E, you'll have this 90% appears over here. So I don't know, hope you enjoyed it. And you stand this slightly less than traditional way to teach this course, and I had fun, and thanks everybody. Thanks for copying, and we'll meet various times, and I'll be valuable until the midterm. Yeah, go home, bye.